Hello, everyone. I'm Haoyu Ji from Harbin Institute of Technology, Shenzhen. I'm glad to take a few minutes to introduce my paper Spectral Scalpel, Amplifying Adjacent Action Discrepancy via Frequency-Selective Filtering for Skeleton-Based Action Segmentation. Our work focuses on Temporal Action Segmentation, which assigns action labels to every frame in untrimmed videos. It has broad applications in fields like healthcare and industry. Specifically, we study skeleton-based TAS. By parsing motion through skeletal sequences, it offers a lightweight and robust alternative to video-based methods. Existing methods have made notable progress by leveraging spatio-temporal modeling, which captures spatial dependencies among joints and temporal correlations across frames. However, current STAS methods still suffer from two critical limitations: interclass confusion and boundary ambiguity. These issues stem from a fundamental dilemma. Models like TCNs and transformers essentially act as low-pass filters. While this over-smoothing effect is great for maintaining action coherence, it inadvertently obscures the essential discrepancies between similar adjacent actions. Therefore, our motivation is to explicitly capture and amplify these core differences to compensate for this architectural deficiency. To break this bottleneck, we pivot our perspective to the frequency domain. Fundamentally, skeletal motions are just joint oscillations. While different actions share common frequencies, they also possess highly unique spectral signatures. Because standard temporal modeling erases these subtle unique cues, we must explicitly amplify them. Point to the figure. As illustrated in Figure 1, we selectively filter the motion spectrum. By suppressing the shared components and amplifying the action-specific frequencies, we successfully enhance interclass discriminability and perfectly sharpen the transition boundaries. Motivated by this insight, we propose Spectral Scalpel. Unlike previous blind data-driven filtering, our approach performs active spectral editing guided by explicit objectives. As shown in figure, you can think of it as a surgical procedure. Our scalpel is the MASF module, which transforms and adaptively edits the frequency spectra at multiple scales. Our surgical objective is the AADL loss, which explicitly maximizes the spectral discrepancy between adjacent actions. Additionally, we introduce FACM to capture frequency-sensitive interactions across channels. Extensive experiments demonstrate that this framework achieves state-of-the-art performance across 5 challenging benchmarks while maintaining high computational efficiency. To summarize, our work makes 3 key contributions. First, Spectral Scalpel pioneers the integration of frequency domain processing into STAS, successfully sharpening transition boundaries. Second, we design a discrepancy-guided filtering mechanism. By combining MASF and AADL, we actively guide the model to learn highly discriminative representations. Third, we introduce the FACM module to strengthen temporal modeling through frequency-aware channel interactions. Ultimately, these innovations enable our framework to achieve state-of-the-art performance across 5 major datasets. This figure details our 4-stage framework. First, spatial modeling captures joint dependencies using multiscale and dynamic GCNs. Second, frequency modeling leverages MASF to adaptively edit the action spectra. Third, temporal modeling integrates global context via linear transformers, enhanced by FACM for frequency domain channel mixing. Finally, the prediction refinement stage outputs the classification and boundary results. For optimization, as shown at the bottom, the entire framework is jointly supervised by 4 objectives. Our proposed AADL, a contrastive loss for semantic alignment, alongside standard CE and BCE losses. Let's dive into our first core component, MASF, which acts as our spectral scalpel. As shown in Part A, it operates in 2 main stages. First, it transforms spatial features into the frequency domain and applies multiscale, multi-head filters to capture spectral components at various resolutions. Second, to aggregate these filtered features effectively, we propose a dual-branch fusion strategy. By combining a static branch for consistent patterns and a dynamic branch for instance adaptive weighting, we achieve highly flexible and robust channel-wise spectral editing. Moving to Part B, we introduce AADL, which serves as the explicit objective for our scalpel. Its goal is to maximize the discrepancy between adjacent actions. To do this, we extract the segments and compute their amplitude spectra. We deliberately discard phase information to ensure shift invariance. By interpolating them to a unified frequency resolution, we can directly compute their absolute differences. Minimizing this loss forces the model to heavily penalize shared frequencies and significantly amplify the unique spectral signatures of adjacent actions. Finally, in Part C, we introduce FACM. While linear transformers handle time-domain interactions, FACM is integrated to model cross-channel interactions directly in the frequency domain. We first split the complex spectra into real and imaginary components. Instead of processing them independently, we concatenate them and apply shared pointwise convolutions. This strategy is mathematically equivalent to a direct linear transformation of the complex spectrum. It maintains spectral integrity and complex linear plasticity while remaining highly parameter efficient. Next, let's move on to the experiments. We evaluated Spectral Scalpel on 5 diverse public datasets, ranging from daily activities to fine-grained sports. To measure performance alongside frame-wise accuracy, we specifically focused on the segmental edit score and F1 scores. As noted at the bottom, these segmental metrics offer a more comprehensive evaluation by strictly penalizing the oversegmentation errors commonly seen in this task. Here is our comparison with state-of-the-art models. Spectral Scalpel consistently achieves the best performance across all 5 datasets. Specifically, on the rigorous F1 at 50 metric, we gained an impressive 4.8% on PKU-MMD. Importantly, we achieved this with lower computational costs and fewer parameters than previous top models. Moving to the qualitative results. As highlighted by the red boxes, existing methods frequently struggle with misclassifications, boundary shifts, and under- or oversegmentation. In contrast, Spectral Scalpel produces predictions that are much more closely aligned with the ground truth. This visual evidence clearly highlights the superior capability of our discrepancy-guided spectral filtering and channel mixing mechanisms. Finally, figure shows the TSNE visualization of our representation space. While baselines like DEST and LASA exhibit entangled feature distributions, Spectral Scalpel yields highly compact intraclass clusters and clearly separated interclass regions. This proves our filtering mechanism fundamentally enhances feature discriminability. Let's look at the ablation study. As the table shows, integrating MASF, AADL, and FACM individually yields consistent gains. Combining them confirms their highly complementary nature, culminating in our best-performing full model. Importantly, these modules add minimal computational overhead, with AADL being completely cost-free during inference. Finally, to understand how our model works, let's look at the feature activations in figure. Without filtering, adjacent actions exhibit highly entangled and similar patterns. However, as seen on the bottom, our filtering successfully suppresses shared low-frequency components and amplifies unique amplitude variations, perfectly validating our original motivation. To conclude, Spectral Scalpel pioneers the integration of frequency domain analysis into STAS. By combining MASF, AADL, and FACM, we effectively amplify interclass discrepancies and achieve state-of-the-art performance with high efficiency. Moving forward, we plan to address remaining boundary challenges by exploring adaptive local filtering and contrastive frequency learning to further enhance model generalization. Thank you for your attention. That concludes my presentation.